In this video, I'm going to show you three things. First of all, I'm going to show you how to use the pfft object in order to take an incoming audio signal and represent it in the frequency domain, displaying it as a sum of different frequency bands and their amplitudes together. Secondly, I'm going to show you how to create a scrolling histogram based on this idea. In fact, you can see it right here at the bottom, which is a history, a scrolling history of these FFT, fast Fourier transform analyses. And lastly, I'm going to show you how to create a 3D shape that is affected by these analyses. So a 3D shape, 3D visuals that show you the frequency domain as it evolves and changes over time. You can use this to create all sorts of cool visuals and audiovisual ideas. Let's begin. So I'm feeling quite ambitious today and I want to do three things. First of all, I want to represent the incoming sound in the frequency domain visually. Secondly, I want to have a scrolling view of this frequency domain analysis, which is also going to be visual. And last but not least, I want to represent this data in 3D visuals. So let's start with the first one. And to do this, I'm going to use the easy ADC object, if I can type it right, which is going to receive the audio signal coming in from my microphone. It's going to be sent out from the very first outlet. And now I need to use the pfft tilde object to process this sound, turn it from time domain into frequency domain to get data on how much amplitude each frequency band has, so that I can create some kind of spectral graph of the incoming sound. And as cool as this sounds, this will not immediately work. It's going to be like this. You might think this object does not exist, but that is not the problem here. With pfft, you need to always refer to an external patcher that you have created, and that is going to be loaded into this object, and then that object will run inside pfft. So let's quickly create a new patcher and see what we can do. Alright, so I need to use two specific objects here. The first one is FFT_in, short for fast Fourier transform in. If you don't know what fast Fourier transform exactly is, that is fine. Right now I'm not concerned with the finer details of this world of mathematical signal processing. I just want to visualize the frequency domain. And this FFT_in will also not work on its own. We need to give it as an argument which inlet it is going to use in the pfft tilde patcher. And it's going to use the first inlet. If I want, I can create a complementary FFT out tilde, again with the argument of 1, which is going to send out whatever's coming into these inlets from the outlet of pfft, but I will not be worried about that right now, because the output must be some kind of visual data, ideally a jitter matrix. In fact, I can create this right now. So jit.matrix, let's see, let's also give it a name. Let's call this analysis, and I will give it one plane. I'll give it the data type of float 32, and I will give it the dimensions of 1 to 1. Let's keep it 1 to 1 for now. We will see in a second what exactly we need to do with these dimensions. So if we go back to FFT_in here, you'll see that it has 3 outlets, and we are concerned with the first 2. The first one will send out the real input 1. The second one is the imaginary input 1. So these are the results of the fast Fourier transform analysis. Again, not very concerned right now with what this mathematically means, but I just know that I need to use the cartopol tilde object to transform this data into something a bit more meaningful. So I'm treating these as Cartesian coordinates and I'm transforming them into polar coordinates at signal rate. And what this does is that it sends out from the first outlet the amplitude of each bin that is getting analyzed. And that is an integral part of the fast Fourier transform analysis. This algorithm will analyze a window, so a bunch of samples at once. The size of this window is something we will determine ourselves, but the bigger it is, the more accurate it is, but slower it is going to be. And this first outlet of cartopole is going to tell us the amplitude of each element in this window, which will correspond to a certain range of frequencies, showing us how much energy there is at that range of frequencies, giving us an idea of how the spectral profile of this sound exactly looks. And this is the data we want to have, right? So we want to write this into our matrix. But before we do, let's consider what we need to do with these dimensions. Right now, I want to have something completely vertical, right? I want to have a vertical matrix, so 1 to something, something, something that is as big as the spectral window, as much as the amount of data I'm going to receive from my pfft patcher according to the window parameters I give it. And to process this information, there is this very useful object called pfft_info tilde, which is going to report the information about the pfft patcher when we load it. So when I load this patch in my pfft tilde object in my main patch, the moment it's loaded, these outlets are going to send out something meaningful. The first one, the FFT frame size. The second one, the spectral frame size. And that's what we exactly need. So I'm going to determine the dimensions of this jitter matrix using the spectral frame size. I'm going to construct this message, dim, so I want to change the dimension of the matrix. And I want to make it 1 to $1, meaning whatever is coming in through here to this message. And if I do it like this, whenever I load up the patch, this data is going to determine the dimensions of this matrix. Okay, great. So now I just want to write this information into this jitter matrix so that I can use it outside of this pfft patcher. And I want to write only the amplitude signal here. The second outlet will also send something meaningful, the phase of the incoming frequency band, but that is not relevant for visual processing. We will use this in the future when we want to create cool audio effects. But for now, let's just use jit.poke tilde, which is going to write the incoming audio signal into a matrix of our choosing. But to do this, we need to give it a few arguments. So first of all, the name of the matrix, right? I'm going to write this data in the matrix I called analysis. This matrix has 2 dimensions. It's 1 to 1 or 1 to whatever my spectral window size is. So the second argument is 2. And I am targeting the first plane. And we start counting planes from 0. So I'm going to make the final argument 0. All right, so I'm going to have 3 inlets when I create the object like this. The first one is going to be the value I'm going to write in my matrix. And the second and the third ones are going to be the coordinates of the cell in which I'm writing this data. So the x coordinate is always the same, right? It's always number 0. It's always the first one because we only have one cell in our 2D matrix on the x plane. So I can simply create sig tilde 0. So this will continuously send the value of 0 to this inlet. And for this third inlet, so the y coordinates of the cell in which I'm going to write this audio data, I'm going to use the third outlet of FFT_in, which is going to be the FFT bin index. So each time this amplitude value is coming in, a corresponding value is going to come out of here, telling us what is the number, what is the index number of this amplitude value in relation to the window size. So let's say I have a window size of 512. This is going to be 0, the first value 1, the second value 3, the third value 4, the fourth value, and so on and so on. So this makes it incredibly easy to write these values into the matrix, which is fantastic. And I believe we only need one more piece of coding, which is some kind of output, right? And again, I'm not going to use FFT out because I'm not sending out audio data. I want to send out this matrix. So instead, I'm going to use out with the argument of 1. So now the outlet, the one and only outlet of this pfft object is going to send out this jit matrix. I also want this to happen, when I send a bank to this pfft object. So I'm going to create an in1, not FFT in1, but in1. So when I send data that is not an audio signal into my pfft patcher, it's going to come in through here instead and it's going to trigger this jitter matrix if I send a bang to my pfft object. And I believe this is enough for our pfft patcher. So I of course have to save this, right? I'm going to call this, let's see, frec analysis.pfft. I'm going to save it like this, and I'm going to go back to my regular patcher. Now let's see, pfft tilde, and now as an argument I have to give the subpatch name, which is frec analysis.pfft if I remember right, and then the FFT size, so the size of the window. Because of some mathematical mumbo jumbo, this has to be a power of 2, so let's do 512. Okay, and now it looks like something, right? I can put in audio here. I want to send a bang in here, and the output should be some kind of jitter matrix. So ideally, I can visualize this using jit.p_window. Okay, and I'm going to then start my audio context, and now if I bang this, you can see while I'm talking, if I am clicking this button, if I'm sending these bang messages to pfft, I do see the visuals of my amplitude analysis. And this works from top to bottom, right? So the topmost is the lowest frequency that's possible. The highest at the bottom is our sampling rate. That is the highest amount of the frequency that can be analyzed, I think. And we might then want to flip this down, right? It might make more sense if the lower frequencies are at the bottom. And to do this, I can easily use jit.dim map with the attribute of invert. Then I have to give it 2 values, so 0, so do not invert it on the x-axis, but 1, do invert it on the y-axis. And to make this automatic, instead of having to click this button all the time, I can simply, let's see, create a metro object, maybe metro 33, and then I can toggle that on to continuously get bangs. And now, as you can see in this window, the individual amplitudes of certain frequency bands are being visualized. We are seeing frame by frame the frequency domain, which is the first thing we wanted to do. So that's fantastic, isn't it? I can simply write done here and put some exclamation points because I'm really excited that we got this working. Okay, so what's next? Now I want to have a scrolling view of this frequency domain analysis. I don't want to just see a single snapshot, just a single window, but I want to be able to see something that maybe scrolls by, that scrolls forward as new data is being fed. And this means I have to work a bit further with jitter matrices, right? I have to use a certain kind of trick. So let's see, I want to first have another jitter matrix with another name. Let's call this the spectrum. Doesn't matter what we call it really. I'm going to give this 3 planes because eventually we are going to use this for 3D visuals. Let's also make this float 32, and I want to give this a few more dimensions, right? Not a few more dimensions, but a few more cells. So I want it to have, let's say, 250 cells on the x-axis, and once again my window size on the y-axis. In fact, not my window size, but I want my window size divided by 2 because, again, because of some mathematical mumbo jumbo I'm not going to get into right now, this fast Fourier transform analysis is going to consider half of the window size. So if I'm giving it a window size of 512, it is in fact going to process 256 elements. Right, so this outcoming matrix has in fact a y range, a y dimension, a vertical dimension of 256. We can also confirm this by creating a jit.fps GUI, connect it like this, click on dim, and there you can see this matrix is 1 to 256, not 512. But again, the reason right now doesn't matter. I just want to be a bit practical and I want to visualize the results, the last 250 FFT analyses in this matrix. And like I've said, to do this, I'm going to use a trick. So I'm going to create a copy of this jit.matrix spectrum. So if I give it the same name, these two are the same matrix. If I do something on one, the other one is going to have the same result. And I will process this using jit.convolve. what jit.convolve is going to do is it's going to receive this jitter matrix. It is going to look at some kind of cheat sheet, what is called a kernel, which is also a jitter matrix that is being sent into the second inlet. And according to this, it is going to do some operations and send out a new jitter matrix. Let me explain that a bit better. So let me create what is called a kernel. So I'm going to create yet another jitter matrix. This is going to have one plane, again float 32 data type, but it's going to be 3 to 3, 3 by 3. And I'm going to, by writing a very specific message, which is set cell 0, 1, val 1 dot, comma, bang. I'm going to fill up this matrix with some specific value. So this is going to give the value of 1 to the cell at the coordinates of 0, 1. And then comma bang is going to make sure a bang message is sent afterwards, which triggers this jitter matrix, the output of this jitter matrix. And it gives us this nice shape, right? But what does it mean for jit.convolve? So when jit.convolve looks at this kernel, and then when an actual, the matrix that we want to process comes in, it does an operation on all of the cells. It considers that cell, the one that's being operated on, the middle of this kernel, and depending on which cells have values above 0, it copies those cells into its middle. Essentially, what this does, what my setup right now does, is that it looks at every cell looks to their left, because it's the cell that is to the left of the middle, right, that has the value of 1, and it copies that. Practically, this shifts everything to the right by one cell, and if we do this on every step, if we do this on every bang, we are going to have some kind of feedback loop where the matrix itself is scrolling. So when this jit matrix spectrum goes through jit.convolve, I want to put the results also in jit matrix spectrum, which is going to create this feedback loop. All right. And as I do that, when new values are coming in through here, I want to load it up in my spectrum jitter matrix, but only on the left side. So I have to again use a specific trick, which means I have to use a few attributes. First of all, I want to use dstdim, use destination dimensions, which means I will specify what happens, where exactly the incoming matrix goes in this specific matrix. Then I'm going to give the attributes, let's see, dstdim start. So when a matrix is coming in, start placing it at, let's say, 0, 0, so the top left, and then yet again dstdim end, and finish putting in this matrix at the dimensions of 0 to 255, so the bottom left corner. So really place it on the leftmost side of my matrix. And if I do this, right, now if I have another jits p window, and every time this comes in, this doesn't work. Why doesn't this work? Because I did not give the use dstdim attribute the value of 1. I did not turn on the use dstdim function. And now it should work. And if your video quality is high enough, or if I zoom in here, you'll see that this always appears. The new info always comes into the leftmost block, the leftmost horizontal block in my matrix. Right? And now to have the scrolling effect, all I have to do is to make sure that when this metro sends out a bang, it happens like this. So each bang triggers 2 bangs. First of all, I send out my current spectrum jitter matrix. I put it through this convolve procedure, meaning everything shifts back to the right, and then I send the result to the same matrix, jit matrix spectrum. And after that, I trigger my pfft, which means that the leftmost block is now my latest FFT analysis. And you can see what is happening. We have this really nice scrolling visualization of how the frequency domain evolves over time. And we can really use this right now. Let's go to the third step. So I'm going to write yet again done. This time I'm going to put 4 exclamation points because I'm really excited that even this worked without me having to do 20 unique takes. And then here we are representing this data in 3D visuals. So of course, if we are doing 3D visuals, we have to work with jit.world, right? Let's give jit.world a name. Let's give it the name of frick visuals. Right, and of course I'm going to give it the attributes of floating 1, and FSAA 1 to make sure my window is always at the top and my visuals, the quality of the visuals, are as good as they can be. And when I toggle the sun, of course, I really don't need this metro anymore. I can simply use the second outlet of jit.world, which is going to send out a bang per frame, which is a really nice way of syncing up the visualization process with the calculation process. Okay, now to visualize this, let's use jit.gl.mesh. Let's use this Jitter Matrix as the raw data to create a 3D shape and maybe some colors to go along with it. So jit.gl.mesh, right? Jit.gl.mesh, I have to write in my context, my jit world context name, which is frec visuals. And then I'm going to give it the draw mode attribute of line underscore strip. This should work if I remember it right. And of course, nothing is going to happen right now. This jit.gl.mesh is expecting some kind of matrix data. And if I simply put this in, this will not work because even though this looks very good visually when it's projected onto a square, if we try to implement these values as coordinates, I'm just going to get this singular diagonal line, which does not look really that interesting. So let's turn back to our old friend, jit.gen. Let's try to process this incoming matrix. Right, so as you know, jit.gen, the world of gen, a bit different than our max patching world, but not so really. The only thing we have to know is that when I define something in jit.gen, every cell in the incoming matrix gets processed simultaneously, one by one or simultaneously, doesn't matter, but this operation will be applied to every cell in this matrix. And when I connect this to jit.gl.mesh, right, I can simply use snorm to get the normalized coordinates. So each cell gets a value from -1 to +1 on both dimensions. I can use the Swiss operators, Swiss x and Swiss y, split these two values, both going from -1 to +1 apart, and I can pack them into a vector that has 3 planes, which means this becomes the x coordinate, this becomes the y coordinate, and the z coordinate stays at 0, which is going to give me this nice plane. I can also look at this by using jit.gl handle, right? I can create jit.gl handle, connect it here, and then I can use my mouse to control these visuals. Okay, so this is cool and all, but this is just a plane. So why don't let's try, for instance, to use the incoming value, so the actual amplitude of each cell here, as the z value, which should be between 0 and something higher than 0. Well, okay, and as you can see, we immediately get something cool. It's pretty high, so we might want to fix this, that is a bit more concentrated. But if I zoom in, you can see that the analysis of my audio is being represented here as this 3D shape, which is really cool in and of itself. So to make this not as tall, maybe I can multiply this incoming value with something less than 0 to scale it a bit down. Let's say 0.1, multiplying this by 0.1. And this looks a bit more manageable, but still a bit boring and gray, doesn't it? So I can also use out2, so I can have a second output of this jit.gen object, and I can simply just send the incoming data to this second output, just to see what happens. And then I can connect the second outlet of jit.gen to the color inlet of jit.gl.mesh. So that's the fourth inlet. And now it's colored according to how strong the amplitude is for each frequency band. So it immediately looks a bit better. To accentuate the strong areas a bit more, I can multiply the incoming values with something higher than 1. So I can actually multiply it by, let's say, 10. And it will look like this. So now we have a nice visual representation of our audio analysis. I can even flip this around, look at it sideways. Now it looks like a terrain, right? So for example, it might be interesting to work with this on the level of terrains. Maybe you can have some different colors here for different frequency bands, or something determines the colors. Maybe this offsets an already existing shape. And finally, as an example, maybe we can try to use jit.gen to generate a shape along with these datas. What I mean by that is I can use the sphere operator or object in jit.gen, which will give me the coordinates for a sphere, right? If I only do the x and y coordinates, I'm already getting this really cool spinning disk, which might be useful to you. But I can also get the third coordinate coming in from sphere, so that's Swiss Z. And that will create the coordinates for a sphere. Right, so sphere, I unpack Swiss X, Swiss Y, Swiss Z, so the 3 planes are packed out and then put together, which means now I can, for example, subtract the incoming amplitude data from the Z-axis. And if I flip this around, this creates this really cool planet that is spinning really fast, right? Maybe we can try to slow this down a bit. But I don't really know how to slow it down off the top of my head. Never mind, I found it. So one thing I can do to slow the sphere is to simply limit the speed of the bangs that are coming out of jit.world into this whole algorithm. So a very fast and dirty way would be to use speedlim, which will limit the speed of the incoming messages. And then I can give it, let's say, 50 for every 50 milliseconds, just lets the messages through every 50 milliseconds. Which does make it a bit janky, so maybe instead of 50 we can use 33. There we go. Now it looks a bit better, it looks a bit slower, and later on you or me or other people can discover ways to make this slower. But in any case, there you go. We have visualized the incoming audio into the frequency domain. We have visualized it on a singular jitter matrix. We have created some kind of histogram of this analysis as well. And not only that, we have applied this onto a 3D shape using jit.gl.mesh. So you can hopefully create all kinds of cool installations, ideas, performances using this idea. Thank you for watching.